Now, next talk, Martti Raidal, high spin dark matter.
Thanks for the invitation and thanks for the possibility to talk. So I will change the topic a little bit. I will talk about non-conventional form of dark matter, namely higher spin dark matter. The reason for such a topic is that we recently proposed the effective field theory for performing computations with higher spin fields. And in this talk, I apply this new EFT for computing dark matter abundance. We have written a series of papers. The results, what I will report here, are all published in the first paper, and the work is done together with my postdocs and colleagues, Juan Criado, Nico Koivunen, and Hardi Veermaa. Okay, here is the outline. I will spend quite a bit for motivating the topic, why higher spin particles. And then I will present you elements of the effective field theory for performing computations with higher spin fields. I believe here I have something new to say, namely that computations with higher spin fields can be consistent and can be easy. Then I apply the theory to compute freeze out, freeze in, direct, indirect detection of dark matter, collider constraints. And here my main result will be that that higher spin dark matter behaves very much as a WIMP. Okay, quantitatively the interactions are different. There are interesting quantitative effects, but qualitatively you can think of this as a WIMP. So no way to solve Hubble tension in this model or in this framework. Okay, let me start. So what concerns the spin of particles, there are powerful theorems. There are powerful theorems which tell that fundamental massless interacting particles must have a spin equal or less than 2. And in particular, there is only one graviton, namely one spin 2 field, massless, which couples universally. And this indeed makes a lot of sense because particles with spin 0, spin 1/2, spin 1 have been discovered. We have discovered also gravitational waves, so most likely a graviton exists. There is one particle in this list, namely the spin 3/2, which is missing. Because we know that there is a dark matter, it could be, and some people speculate that the dark matter has a spin 3/2. So this is an interesting possibility. I will not speculate on this anymore, but one can keep this in mind. So there is a generic, if one looks theories of these particles, there is a generic pattern, namely the higher is the spin, the more complicated is the theory, the more constraints one has to put on the theory to make a computation or to the theory to make sense physically. So for example, you consider gauge bosons or spin 1 fields. It is commonly believed that in UV complete theories, these massive spin 1 fields must be gauge bosons. Okay, now if you go to higher spins, it becomes even more complicated, theories become more certain. However, if we talk about dark matter, we know that dark matter must gravitate, which means it must be massive. So these theorems do not apply because these theorems are apply to massless particles only. So in principle, dark matter can be composite, for example, and dark matter can have any spin. So what is the motivation for higher spin particles? Okay, the most important one, in my opinion, is the most general one. Why not? I mean, we in the present stage in particle physics, we don't have any more well-accepted theoretical guidance for new physics. We used to have one, which was naturalness. So we studied SUSY, we studied all other theories. These were not discovered. So one has to study every possibility and perform every possible computation. So in my opinion, higher spin particles represent a good class of new physics good class of new physics, so one has to study. On top of that, we know that higher spin resonances actually exist in hadronic physics, and these must be described. So there are problems with these theories. Maybe one can improve them. Going to wilder speculations, string theory predicts towers of higher spin fields. So perhaps they can be indeed present in the nature, or recently I discovered a paper discussing that if dark matter is produced by inflaton in the early universe, it has a lower bound on its mass given by Hubble parameter. So this dark matter must be super heavy. So super heavy, the higher spin fields may be super heavy. Again, one needs a theory. So in any case, these particles are well known, and there are problems associated with computations with these particles. So I give you examples. I give you two examples, both related to spin 3½ particles. Okay. First is the gravitina. So the Raidal-Schwinger field was proposed long time ago. It's in a Lorentz representation 1/1/2, and it is described most commonly by vector spinor. So object with one Lorentz index and with spinor indices. So now, if one studies a little bit more carefully, one finds that it contains spin 3½ degree of freedom and unphysical spin 1 field. Now, free theory with Raidal-Schwinger field is completely consistent, it's very nice. But if you study a generic interaction of Raidal-Schwinger field, the theory is in general inconsistent because the unphysical spin 1 fields start interacting, and generic theories involving Raidal-Schwinger field are actually sick. They cause causality violation and unitarity violation. And in fact, there is only one known theory, which is a supergravity, in which Raidal-Schwinger field is completely consistently interacting. Of course, SUSY imposes all the constraints and cures all the problems. And in this theory, the spin 3½ field must be identified with gravitina. Okay. The second example is QCD resonance, delta resonance. So delta resonance has spin 3½ and its mass is almost the mass of proton. So in order to describe this resonance, one uses the theory which is at hand, which is a Raidal-Schwinger theory. But the problem is that if you use generic couplings, this delta resonance couples to nucleons, pions, photons. If you use generic couplings, the unphysical spin 1½ background starts to interact. One has to remove them from the interaction. There is an entire branch of science which is dealing with these couplings which are consistent. Basically, people invent couplings in such a way that only spin 3½ component of the Raidal-Schwinger field interacts and the spin 1½ component does not. So our theory, our EFT, what we have proposed, can be actually applied to this problem as well. And last week we published a paper how to compute delta resonance interactions consistently. But this is off the topic, so I will continue with cosmology. So there are problems with higher spin fields. Okay, how to deal with them? The idea goes back to Weinberg, so it's not our idea. And what Weinberg suggested is that use Lorentz representations which contain only physical higher spin degrees of freedom. And what he proposed is that to use representations J0 plus 0J, and here J is any spin, can be 0, can be 10. Okay. If you now study the degrees of freedom carried by these representations, you find out that there are exactly the right number of degrees of freedom to describe the higher spin field and nothing else. There is no unphysical degrees of freedom in these representations. And this representation can describe a Dirac or Majorana particle depending what do you choose. Okay, let's see the known particle, how the known particles fits to this picture. The Higgs boson, of course, is a trivial, it's a 0-0, so it's a trivial example, but standard model fermions, left and right fermions, nicely fit to this picture. However, the gauge bosons in the standard model are described by representation 1/2, 1/2. So if you have a UV theory, UV complete theory, the theory chooses. The same applies to gravitino, as I already discussed. Gravitino is 1/1/2, and the graviton is not 2-0. It is something. So if you have UV complete theory, the theory chooses which representations you have to use. But if you are interested in studying phenomenology of higher spin field, just pure phenomenology, one can use these Weinberg representations. For example, rho meson is a spin 1 object. So for describing this theory is okay. Dark matter, if dark matter is composite, this theory is okay. Or any other generic massive higher spin field, which comes from string theory, for example. So Weinberg continues. So this theory does not have a Lagrangian description. So what he does, his starting point was to take equation of motions instead of Lagrangian. So there are two sets of equation of motion, Klein-Gordon, of course, and then something which is equivalent to Dirac equation. The first gives conservation of momentum and energy, and the second describes then the movement of particles. And here the psi is a higher spin field, which is represented in the usual way in plane waves. So for higher spin, this second equation of motion has several derivatives. So some people interpret that there is a coast. No, there is no coast, because this propagator, if you derive the propagator, has one pole. In the case of coast, there are several poles, and there is a minus sign in front of the propagator. Here, the propagator has a funny shape, but it really has one pole. Okay, it's a more complicated theory, but there is no coast. And as I said already, there are external legs, external particles, which are described very much the same way as in normal field theory. So this is the free theory. And this is an example that one can write down the Feynman rules for a free theory in a consistent way. One can also include interactions. And interactions can be included using effective Hamiltonian. So now which interactions you use depends on your problem at hand, because I'm interested in studying dark matter. Here I will study Higgs portal. So namely, Higgs portal is the simplest interaction what you can write for two higher spin fields and for two Higgses. This has a Z2 symmetry, which ensures that the dark matter is stable. I will comment on this in a minute. But in this way, this kind of theory actually represents EFT for a generic massive any spin particle. One can write Feynman rules, two perturbation theory, compute interactions. As long as one consistently works below some cutoff scale, this theory is as good as any other effective theory we use in particle physics. And this is an interesting result in the sense that in higher spin field physics, this has been missing so far. So why it has been missing? The Weinberg's paper was published in 1964, I think. So it has quite few citations, but this formalist has not been used for phenomenological calculations. Okay, I don't know exactly the answer, but most likely the answer is that EFTs were not popular in the 60s. They have recently become popular now because of the LHC results. Maybe the second reason is that supersymmetry has been quite popular, and therefore Raidal's finger theory has been more popular. The higher spin fields have been gravitinos, gravitons, etc. But one of the problems is also that Weinberg's original formalism becomes increasingly complicated when you apply this to higher spin fields. And in order to improve on that, we reformulated this theory using multi-spinor formalism, using the two spinors. Namely, people who are familiar with this know that even the standard model can be rewritten in a way that there is no Lorentz indices, there are only spinor indices. All momenta can be rewritten, all derivatives, and all the objects, all the standard model fields can be represented by objects which are multi-spinors, with objects with spinor indices only. Now, the funny thing is that when a standard model becomes extremely ugly and not comprehensible in this way, the higher spin theory becomes actually simpler. And this is what we noticed, simply in the sense that the formalism is the same for any spin. Therefore, one can use this formalism to study physics of any spin. And this is what we have done. So the EFT for a dark matter of any spin is the following. We want the dark matter to be real field or Majorana field. Therefore, we chose the representation J0, just one representation. So, and what we study is the Higgs portal. The simplest possible interaction you can write down is the Higgs portal. It has a complex coupling, and this is important. So, for example, if you consider this is important phenomenologically, because this interaction applies to any spin, so including spin 0. If J is 0. This is just scalar self-interact. This is normal, usual Higgs portal coupling. And there are parity even and parity odd couplings, which correspond in this case to scalar and pseudoscalar. But this concept is general. It can be extended to any spin, and this has important phenomenological consequences. Now, if one writes down this field, one obviously can write down more interactions, not only the Higgs portal, but several others. For example, the linear interactions, which are important for collider phenomenology. For spin 3 half particle, they are both the same, both operators are of the same dimension 7. But if you go to higher spins, the Higgs portal becomes naturally the dominant interaction. All other operators are suppressed by more powers of lambda. So there is actually, for spin 3 half, you have to assume Z2 symmetry to have a dark matter. But for high spin fields, the Z2 is accidental symmetry, which appears by itself in this framework. Okay, given the theory, first thing to compute is to compute dark matter abundance from freeze out. Okay, this is the usual story. One has to solve the Boltzmann equations to compute annihilation cross section, in this case non-relativistic limit, and to compute dark matter abundance. Okay, to do that, we have computed dark matter annihilation channels. They depend on the spin, they depend on the coupling, namely whether the coupling is complex or not. And I will show you the results in a minute. But before I show you the results, we have to include all the constraints. The constraints come from dark matter direct and indirect detection. Here, the direct detection bound from xenon 1 ton is most important. So we have to include it. Again, the computation is usual, and the result is given here. as you see here, the result very strongly depends on whether the coupling is real or imaginary. If it is purely imaginary, what happens, or if it is parity odd, the S wave part vanishes exactly, and the full cross section starts depending on the velocity of dark matter, which means it is strongly suppressed. Now, we also included indirect detection bounds from dark matter annihilation to BB bar and WW. We took them from the most important constraints come from observation of dwarf galaxies, and we took them from the literature. Now, collider constraints, of course, there are two sets of constraints from there. Higgs invisible decays, which apply to light, relatively light dark matter, and then non-observation of missing energy in PP to jet missing energy or the photon missing energy. We computed the processes and put everything together. The results for freeze out for parity even couplings are presented in these two plots. So as usual, the plots are given in dark matter mass against the portal coupling strengths for spin 2 and spin 3/2. The black line corresponds to the observed relic density. The pink area is bound or exclusion bound from xenon 1 ton. The green area is exclusion bound from indirect detection, and the blue bound is from collider. The gray area is excluded theoretically because of unitarity is violated. And as you can see, this result is for spin 2 and spin 3/2. Like most of the parameter space is for parity even coupling is ruled out, the same way as parity even scalar is ruled out. However, if one switches to parity odd coupling, the direct detection bounds are eliminated. Indirect detection bounds switch from boson to fermion case, and the rest is very similar. So in this case, dark matter can be spin 2 or spin 3/2 without any problem. Okay, having a relatively large coupling and the mass of the typical WIMP. If we consider freeze-in, again, the story is the same. One has to solve the Boltzmann equations here. The difference is that it is UV freeze-in. The annihilation cross-section is dominated by very high values of collision energy. So unlike in freeze-out, where the limit is non-relativistic. And the result is also the same anticipated one, namely the coupling must be so small, it must be really, really tiny so that one cannot actually see it anywhere in practice. So this actually concludes my talk. So we have written down and worked out effective field theory for generic massive any spin particle. We use Weinberg's representation, which contain only physical degrees of freedom. We have converted his original theory to multi-spinor formalism, which allows us to write down nice and simple Feynman rules and perform nice and simple computations. All these Feynman rules are published, so if you are interested in doing computations with higher spin fields, you are welcome to join us. In particular, so talking about higher spin dark matter, yes, higher spin dark matter is fully possible. It behaves very much as a generic WIMP. all freeze in, freeze out are possible, and the suppression of direct detection bounds with parity odd couplings is also possible. This feature seems to be general for low and high spin fields. Thank you very much for your attention.
Thank you, Martti, for inspiring talk. Now questions. I don't see any questions. Martti, yeah, just naively, I would expect the same as you written as the last point in your conclusions, that high spin dark matter behaves as a generic WIMP. So that's it. There is no specifics, right, for high spin dark matter.
Okay, this is well. Okay, let me correct it. Yes, if the dark matter is gravitino, then this does not apply, right? So what if you describe higher spin field, higher spin field is a massive, and you describe it with this effective theory, it becomes a WIMP.
Yeah.
Now, if you have a UV theory, like a theory of gravity or something, which automatically contains higher spin fields, then the story can be different. You can have a different effects. But if you have a, I don't know, you have a theory of gravity which contains generic massive spin 2 fields, how do you describe them? This is the effective theory to describe this kind of fields.
That I appreciate, I understand.
Yeah.
And indeed, for massive graviton, we can have a lot of effects. We can see them in the CMB anisotropy spectrum. There are very clear signatures. If we see it, we will know it's massive graviton, but maybe there is something for higher spins even.
So for dark matter was the first application we did, because the simplest possible operator you can write down is the Higgs boson. Actually, this theory is more interesting for collider phenomenology because it predicts very specific interactions. So it predicts very specific signatures, which are completely
open doors for collider searches.
Yes, so
collider searches.
So for collider searches, it has a very concrete predictions for funny signatures, and also, as I said, it is actually applicable to hadronic physics. In hadronic physics, they invent interactions essentially by hand. They check. Once you have an interaction, you have to check by hand whether your computation is physical or non-physical. So our theory is good tool for them. I believe so, because you just mechanically do the computation, and if you do the computation correctly, the result is correct. The result for sure is physical. You don't have to add anything beyond effective field theory.
Okay.
So for hadronic physics, I hope it is usable.
Now we have a question from Valery Rubakov.
Yes, in the first place, I would like to apologize for not being capable of chairing this session because of my sort of sickness. Still, let me ask a question. Which of the hadrons have this property that they belong to J0 plus 0J representation? For example, rho meson apparently does not have this structure because it mixes with a photon. So what hadrons do have this property?
Okay, concrete. My background is not hadronic physics, so we have at the moment studied only one case, which is delta resonance. Delta resonance is the first resonance, and it seems it is one of the most interesting ones. In the sense that it couples to many particles, photons, pions, nucleons, etc. So, for example, we studied this case, and we found out that this can be described by our theory. In fact, just writing down the most general interaction Hamiltonian and applying all the hadronic physics symmetries, we got only one coupling constant for each needed coupling. So it is even predictive. It's a nice theory. Now, whether it is whether this can be applied to spin 1, I don't know. This theory cannot be gauged, or at least the gauge theory of this is very, very complicated. Something non-local, something crazy. We don't know yet. But hopefully it can be applied to higher spin resonances, and there are many higher spin resonances.
Okay, Edward.
Yeah. Dear Martti, first of all, thanks a lot for a very interesting talk and nice ideas. I have such a question. In fact, did you apply all the constraints what we currently have from the Higgs sector in all couplings and all?
Yes. These are.
Comment on that in a bit more detail, or?
Okay, let me go back. So here, yes. So we took the constraints from LHC and applied them as thoroughly as we possibly could, and the constraints are from the Higgs sector are given by the blue area here. So mostly these are from non-observation of missing energy, and obviously invisible widths. The main constraint for light particle is the invisible widths of the Higgs. These are the two things we applied. So perhaps one can do better, but this is for theorists. This is already good enough.
Yeah, because I would think also you should apply some constraints on all these signal strength parameters, which one has already.
Well, because these are not involved in the production. Why do you think so?
Well,
really, it only affects the decays, right?
Yeah. Okay.
I don't know how it can modify the.
No, it somehow it goes through loops and modify coupling constant. But okay, I know it just.
Okay, we did what we did, so one can always improve.
Okay, thank you.
Thank you.
Okay, I don't see more questions. So thank you, Martti, once again for inspiring talk.
Thank you very much.